Hey everybody, it's Tom Trams with the FujiNet project. And I had a question as to how the background graphics in the ISS Space Tracker map were actually done and brought into the program. So I will make a quick video showing how I acquired the image, processed the image, and brought it into the program. We can see right here with the ISS Space Tracker that we have a very detailed map. Well, as detailed as a TMS 9918 graphics processor can give us anyway. And you can see that it's not, while it could be made up with tiles here, there are a lot of details around the edges that would make it very difficult to come up with one single concise set of tiles that would look good in all cases. So we use a variant of the graphics mode here called Bitmap mode to take and produce this image. And I'm going to show you how I took and made the images in the first place. We'll go over here to my desktop here, and the first thing that we'll actually bring up is I'm going to take and do a small explanation as to how this particular graphics mode actually works. And for that, we'll actually just bring up the technical documentation for the 9918. I'll go into my Documents folder, select Chip Documents, and bring up the TMS 9918 data book here. And this is, if you're doing any sort of programming for this graphics processor, this documentation is absolutely essential. It provides all the information that you need to take and use all of the features of the chip. We're going to go to section 2-19, which briefly describes the graphics 2 mode. And if we get here, you'll see just before that, you'll see a little bit about the memory map and how the memory map relates. And that is good reading as well. But if we come all the way down to 219, we'll see a mention of what's called Graphics 2 mode. And as it says right here, what it essentially does, which is instead of in Graphics 1 mode, you have 256 tiles. In Graphics 2, you have 768 tiles that are arranged in rows of 32 with columns of 32 with 24 rows. And each of those pattern tables are arranged in memory such that the first 256 tiles take up the first third, the second row of 256 take up the second third, and the third set of 256 take up the bottom third. We're going to use that to our advantage by taking each of those patterns, 0, 1, 2, 3, 4, 5, 6, 7, etc., and laying them out exactly as they're seen here, so that we can, by changing the composition, the patterns of each of these tiles, we can do bitmapped graphics. And we're going to use a little tool to help us along in the process. So the first thing I did was I went to a stock photo site and found an absolutely fantastic world map. And this world map happened to be downloadable in EPS format. EPS is encapsulated PostScript format, which is a nice vector graphics format, very high resolution and can be scaled to any target resolution that you would need to. So it works out really well for our purposes. And if you look from the thumbnail here, you can see that this is a black and white image. We can take a look at it. We can see it's a nice, very detailed graphic. And as I take and resize it and move it around, you'll see that it maintains its fidelity because these graphics are vector. They're comprised of lines. Very easy to take and to size to what we need. And as you can see, it's two-tone. The land masses have one color and the water has another. This is very good for our purposes. We'll go ahead and open that up in GIMP, which I think, yeah, I'll just do it from here. And then we load the image. We go ahead and accept the defaults, which they're fine. And we now have a bitmapped version of the image sitting inside of GIMP here. Since this image is very large, it can be scaled down quite effectively. All we have to do for the first pass of this is essentially just take and scale the image down to its target size. Now, if you recall, if I still have it here, yes I do, let me bring it up. You'll see that we didn't scale the image to fit the display exactly. What we actually did was we left 4 blank rows down below so that we could do the status display down here. So we need to do the same. The target resolution for the ColecoVision is 256 by 192. And to remove the 4 lines, we need to subtract those numbers of that number of pixels. So that brings the image down to 256 by 160, which is our target. Just fine. We'll put this away for now. So we go ahead, 256 by 160, making absolutely sure that we are not constraining the image. We don't care about any sort of warping that may happen, so we'll simply scale this with the defaults. We wind up with our target image. Let's go ahead and zoom in so we can see it a bit better. It's going to take on some graininess because, of course, now the image is much smaller. But that's okay. Just fine. All we really need to do now at this point is to select. And in fact, I'm going to do one better here. You'll notice that I selected the default interpolation, which anti-aliased all of the edges here in an attempt to make them look smoother. This is actually going to work against us in our favor here, against us here. So we'll undo the scale. You'll see that the edges are nice and crisp here in the original. So what we need to do instead, when we scale our image, is to set to none so that we don't try to do any interpolation at all. And you'll see because this constraint was set, it tried to adjust the height to fit the width to maintain the aspect ratio. We don't really need to do that here. Let's go ahead, make sure our interpolation is set to none, and we scale it. Now you'll see all the rough edges are gone, but the edges are a bit rougher. That is okay. But we still have a 1-to-1 relationship between the background and the foreground color. So far, so good. And now, what that remains for us to do is to select our particular colors that we want to use. For the background, it's really simple. We'll just set blue as far to the right as we possibly can, and that will give us our water. And we can take now and do a selection by color. Select the background here, drop the background color directly on, and there's the color for our background. For the landmass, though, we want to use a color that is very green, so it gives us a nice contrast. Now, I'm going to skip ahead just a little bit here. I initially did this as far green as it could possibly go, and the conversion tool gave me the dark green as a default, which really didn't fit well with the contrast of the colors because it picked the lighter blue as the default background, as you see in the target image. So what I did was take this dark color and then increase the chroma until I wound up with this color right here, a nice bright green. I take that, I invert my selection because I know for a fact that any color that's not water as a landmass makes it very easy to deal with. I invert my selection. You can see that nothing changed, but it actually did. We'll see now that when I take and I drop in green, that we get our final target color. So far, so good. At this point, we can save, export, and export the image. I'll go ahead and put this into this folder here and call it a ping file. Boop. Export. We're done here. We can simply take and discard any changes here since I have the original source here and I have the target image, which I've done. For the next bit, I'm actually going to use a tool called Convert 9918, which you can get from GitHub. Convert 9918 is a wonderful utility which takes and converts bitmap graphics such as those from Ping or GIF or bitmap files and converts them into a format that the TMS 9918 can understand, especially for bitmap mode. Although it does actually support the other modes as well. It even supports the multicolor 64x48 mode. It's a very useful tool. And there just happens to be a distribution version of it that you can download. You can grab this, pull it down, put it into a folder, and use it immediately. We'll go ahead and come into it. You can see our source image right there, Convert 9918. This loads up to a simple program. There's a console in the background which you can use for showing debug information. If everything's working right, you won't need to use this, but it does help if you're needing to debug what's happening with your image. We can open and go to that folder, my Convert 9918 folder, and pull up the map ping. It converts it. There we go. And actually, I need to make one small change here. I made one small mistake. Let me close this real quick. I will load the map ping here. We will zoom in ever so slightly. And I need to leave a space down below for the text window. Canvas size, 192. Leave an area down below. Fill it with the background color. That never seems to work. It's very strange, but okay. I can fix that, no problem, just by going into the layers, adding a new layer with background color, and putting that behind. And so now we have a space down below for our status display. Let's go ahead, overwrite. And we can come back into Convert 9918 and do the conversion again. Come back in here. Now you'll notice that it's trying to dither the image to get more color out. We don't need that. We want to hit none. We want to reload the image. And you'll see that it has gotten rid of the dither pattern. Chosen the light blue for the contrast here, which is fine. But our land masses are now gray because it interpolated a bit too far. We can fix this by changing the gamma correct to half of what it needs to be. We reload the image, and we see our final. Now, of course, once this is done, you can see the save pick, and we can save out the resulting work. Going into the workspace again, and I'll put it here just for illustration. And we have a few choices for file formats. The ones that are most useful to us are the raw files output, and the ColecoVision cartridge output. We'll save those. And then we'll see here that we have a ColecoVision cartridge that we can load into an emulator onto the real hardware, which will simply display the image as it is. And we can use that, for example, for display testing. Very useful. But even more useful here, we have two files that have been created, which correspond to the color memory and the pixel memory. These two files can be converted very easily. We come here, you can see these two files here. And if we take a look at what each of these files are, let's take a look at them in the hex dump. We'll see that they are very regular. And if you're familiar with how the color information is stored, the bitmap mode allocates each 8x1 area of the screen to have its own unique color space, the background and the foreground. So this data can be loaded directly into memory. We also have, that's also roughly the same size, the pixel data, which corresponds, each of those corresponds to 1 bit on the screen being plotted for each pixel here and packed into the appropriate byte. We can use, for example, a little tool called XXD to take the color information or the pixel information and convert that into a format that C can understand. C include for file format, which just takes the data, packs it into a variable for us. Very handy. Love you. So, same thing for the pixel data. Very easy. So all we really need to do at this point is put those into a file. And now we have our map data that we can put directly into the program. Once this is done, we can go directly into, let's see, FujiNet Apps, ISS Tracker, add them here, okay. And we can see that I've taken that same data and popped it into here. Ready to go. Both the color and the pixels. Well, how are they displayed? Very simple, actually. All we have to do is copy that data directly into the VDP memory. And in C, we can do that with 2 lines of code. And that's it. That's literally how I did it. So Until next time, guys, have fun.